Okay, very good. So we have Sayan who will be talking about Lefschetz fixed point theorem. Sayan, go ahead.
Okay, let's introduce our setting now. So M is our compact manifold, and E and F are vector bundles over M. Now we have a partial differential operator of order T. Now, so this would locally look like a matrix with entries like this. Excuse me. So now we have the leading symbol of this partial differential operator, which is a map from the symmetric power of the cotangent bundle tensor E to F, and can locally looks like the top order entries, and where we replace del x by psi to the power alpha, and this transforms as the symmetric power of this cotangent bundle. Okay.
Can I ask a question?
Yeah, sure.
So E and F are vector bundles over M. Is that what you mean?
Yeah. Vector bundles over.
Of what dimension?
That is not important.
Okay.
If E is of dimension n and F is of dimension m, then this will be a m cross n matrix with entries like this.
Okay, thank you.
So this should really look like this. Now we'll call P elliptic if the sigma L is excuse me, is invertible. And we have a generalization of this, which is an elliptic complex produced here. So what this consists of is a set of VK vector bundles over M, and
I think one should say that for C different from 0, it's invertible.
Yeah.
Because at C0, the matrix is actually 0.
Yeah. Is this okay?
Yeah, that's fine. Yeah.
And you have maps PK from VK to PK. These are partial differential operators, and this is an elliptic complex if, first of all, complex implies that pk compose pk minus 1 equals to 0 as usual, and ellipticity. So this in particular implies that if you take this symbol, then also this is 0. And we call this complex elliptic if at the level of symbols this is exact. That is the kernel is equals to the range. Okay. Now this ellipticity could be checked in another way, which is we consider the Laplacians for this objects, which is just pk minus 1 dual plus pk dual pk from C infinity vk to C infinity vk. So P comma B elliptic complex is actually equivalent to this Laplacian string elliptic. And like as an elliptic operators, we have the Hodge decomposition theorem in this case also, which can be stated as follows. We have the cohomologies of this complex, which is defined usually. That is, this is the kernel of pk range of pk minus 1, and the Hodge decomposition theorem states that this hk p comma b is finite dimensional and is actually isomorphic to the kernel of LK, where the map is phi goes to the cohomology class of phi. And also that L2 of Vk has a decomposition of the form where you have this harmonic representatives image of pk minus 1 and image of pk. This is the introduction to elliptic complex. Do you have any questions? I'll go to the next. Okay. So now we introduce the test of an operator. So suppose Lxy is a continuous kernel function of this of bounded operator Lxy. Now, just Now we have this another operator P, which is, I'll explain the notation. This means this is self-adjoint, elliptic, and positive non-degenerate. Now, this kind of operators P have a discrete spectral resolution, which means that this are eigenvalues of phi nu, and this phi nu forms the complete basis of L2. Now, in this case, we define the trace L2 trace of L summation of L by nu. This is the operator by nu, which is same as integration of trace. This is just saying that it is the same thing to compute the trace over the whole manifold or compute the trace at each point and then integrating it over the whole manifold. But there are some convergence issues here, so we would need something like for K large for this to hold true. Now we define the generalized Lefschetz number, which is the main topic of today's talk. Now suppose we have a map E from M to N smooth, and we have P comma V, our elliptic complex. Then we say T, which is a collection of maps Tk belonging to compatible with P PK equals, that is PK intertwines with this maps Tk. In this case, we define the generalized Lefschetz number to be summation over K minus 1 to the power K trace of T on HK P comma V. Remember, by the Hodge decomposition theorem, this is finite dimensional, so this makes sense. And we have our first theorem, which says that this generalized Lipschitz number is still equal to stress over L2 of Tk e to the power minus T.
Excuse me.
Yeah.
Do you assume that the TKs exist, right?
Yeah. Suppose we have such a Tk, then we can define this generalized Lipschitz number.
And is there any examples of these maps, TKs?
Yeah, of course. So, very good example is, suppose this pk is are your wedge product of the tangent bundle, then product of Tm, then you can just think of this TKs as the pullback maps acting on the forms corresponding to this T. Is that okay?
Thank you.
Also note that in this case I mentioned both the generalized Lipschitz number will just be the classical Lipschitz number. That is, this is a trace of this pullback operator on HKP. This is the Lipschitz number from algebra. And in that case, if, for example, T is equal to identity, then this just gives you the Euler characteristic, which is L, T, P, V, in that case, the Euler characteristic, which was the motivating example for okay, great. So now also,
I'm sorry, I have a question.
yeah.
What is small letter t and what is small letter t?
What is small letter T?
You have a e to the minus t Laplacian, right?
Yeah. So this T, you just choose to be between 0 less than T less than 180. We'll see that this T doesn't matter, but it will be helpful for us to make some estimates here.
So because there is no t on the left hand side of the equation, so are you saying that the trace does not depend on the small t?
Yeah, exactly. Even you take T 0 less than T less than.
Okay.
No, I think the point is, I mean, this trace depends on T, but the alternating sum is independent.
Exactly.
It's the alternating sum, and T can be positive up to infinity, but cannot be zero because it doesn't make sense otherwise. The operator is not trace class at zero. So yeah, I mean, this is one of the beautiful things about the formula, is that it's independent of T, but because of alternating sum, some cancellations happens. Yeah.
Okay, yeah, exactly.
Yeah.
You'll see this in the proof properly. So now this L2 pk you can decompose as the eigenspace as the lambda eigenspace. These are the lambda eigenspaces of, of the Laplacian. And Laplacian was an operator of this kind, PD plus AC, which is easy to see. So we have a discrete spectral resolution of that, and this is the eigenspaces corresponding to that spectral resolution. Now note that pk del k is actually this pk intertwines with the Laplacian as well, because this what is this? This is pk minus 1 dual plus pk dual. So if you add pk here, since this is an elliptic complex, this term will go to 0 and you'll have a pk. So this will go to 0 and you have pk dual pk. And similarly over here also there will be a term like this and another term which will have pk plus 1 pk on the end, and this will go to 0. Hence pk intertwines with the Laplacian. So in particular, pk preserves this eigenspaces pk lambda, and we have this complex which maps pk. And also note that the compatibility condition of pk, which is pk equals to pk plus 1 pk, introduces maps in this sequence. Which commutes because of this condition exactly. Now, for lambda not equal to 0, this ek lambda intersection of, by definition, because this is a non-zero eigenspace, so intersection of eta del k is 0, and we saw previously that this is isomorphic by the Hawes decomposition theorem. This is isomorphic to HKP, V. Hence, there are no corresponding elements of HKP, V here. Hence, this is just this is an exact sequence. So in particular, if we take again for lambda not equal to 0, if we take the alternating sum of this trace of restricted to this ek lambda, then this is a 0 because these sequences are exact and hence the trace will be cancelled in this trace will be cancelled in this alternating sum. This is exactly the reason why the t previously doesn't matter, because now we take trace of tk, trace L2 of tk to the power minus t del k summation over k minus 1 to the power k. Then we'll just take on the eigenspace, and this becomes summation over k minus 1 to the power of k trace of tk lambda to the power minus t lambda, sum over all lambda. Now, in case, now for all lambda not equal to 0, this alternating this by this this alternating sum vanishes, and hence we are just left with summation over k minus 1 to the power k trace of tk 0. And in this case, since lambda is 0, the choice of t doesn't matter. So yeah, that is the nice part. So it doesn't really matter on what we choose t2. So now this is minus 1 to the power k trace of tk on the null space of del k. But again, this is by Haas decomposition isomorphic to hk comma b, p comma b, and this gives you L of t comma b, which is your options now. This is okay. Are there any questions? Okay. So the point here is that this e to the power minus t del k will turn out to be the solution of the heat equation, and hence we can use asymptotics of the heat equation to give some estimates on this Lefschetz number, which we'll do now. Just the equivalent asymptote. Okay. Let's see. So now we add some extra conditions. Suppose the fixed point set of T is union of some manifolds, some submanifolds Ni, and T is non-degenerate, which means that dt restricted to the normal bundle of ny doesn't have one as its eigenvalue. In that case, we have this estimate which says that this trace of t e to the power minus and p is any operator of this form which we introduced earlier, self-adjoint, elliptic, and positive non-degenerate. Then this stress can be bounded by ck t to the power k for t belonging to 0, 1 if t doesn't have any fixed point. And this is your analog of the classic Lefschetz case, where if t doesn't have any fixed point, then the I just write it here. In the classical case, if t doesn't have fixed points, then the Lefschetz number is 0. And this is the same thing here because this can be bounded by ck t to the power k for t belongs to 0, 1. And this k, you can choose to be anything. Just for this k, this constant ck will change. And so if it doesn't have any fixed point, this thing which is the Lefschetz, which is generalized Lefschetz number will just be 0. And we have another estimate which basically in any case gives an asymptotic excuse me, gives an estimate on the Lefschetz number, which is summation n greater than equal to, this is to the power n minus mi t integration over ni, that this ends only depends on finite number of jets of p and t. Okay, let's see. Let's sketch the proof of this given. Mandeep, how much time do I have?
You have about 20 minutes.
Okay, okay. So now we discuss, for the proof, we need to discuss the heat equation in this setting. As before, we have P belongs to, suppose P belongs to D plus and SP, which is self-adjoint, elliptic, and positive non-degenerate. Then over here, the heat equation is plus P H x comma t equals to 0 and limit t tends to 0 h comma t is fx, which is our boundary condition. So in this case, you can see formally the solution should look like something of the form p to the power minus tp. But now we have to make sense of this. Now the idea is from the complex analysis actually, where now since this condition that PD plus SC means that you can bound this P on the real line between minus C comma infinity. The spectrum lies here. So you can draw a cone such that on the boundary, which we call lambda, all the eigenvalues of P lies inside the region bounded by lambda. In particular, outside this region, we have that P minus lambda is non-zero. So we have at least some hope of inverting P minus lambda. But as it turns out, and in this case, we'll define e to the power minus tp with integration over lambda e to the power minus t lambda p minus lambda inverse d lambda 1 by 2 pi. This is motivated from the complex analysis case where you have e to the power minus t lambda here and you're taking 1 by p minus lambda and this give you to the power minus t. But as it turns out, this does not exist always. But can approximate by pseudo differential operators. So what are these pseudo differential operators? I'll not formally define it, but intuitively, what the symbols of symbol of p minus lambda inverse, if it exists, is not a polynomial. So what we do is we take to be we extend the class of symbols to smooth functions in I such that some estimates hold. And these estimates are so that we can define Fourier inversion of them. So, any questions? So we'll introduce the symbols, at least symbols of this file. This is my symbol for pseudo differential operator. So the only we can the symbols of pseudo differential operators, let's call them R n lambda, corresponding to operators R n lambda which approximate A minus lambda inverse. Now, only important symbol for our case will just be R naught lambda, because you'll see there will be some, we can do the estimate just using this. And we have also expressions for R and lambda, but I will not write them because they're complicated and not important for this completion. And now you have En, which is the symbol that approximate it to the power minus Tp. So this will just be the e to the power minus T lambda Rn d lambda. And we have our heat kernel in this case, which is we just do the Fourier inversion of the symbols. En. Now the kernel of T e to the power minus Tp can be approximated by this series, which is exactly the point of introducing this kernel TEN, but this is the corresponding operator for this symbols, which is just yeah. Now, why is this important? Because as we saw before, the trace can be expressed in terms of this kernel. Just integrate over M the trace of x, p dx. This was, if you remember, that the trace could be written by integration of the kernel dx, trace of the kernel dx. It is stated when we define the trace. Let's see. So now this is just by the formula above. This is just this. This again you can write as by a change of variable. Trace of EXEN, where we are using that these ENs are homogeneous. Okay, right. Now, now we'll use integration by parts, which will give us a term the following form. After integrating by parts a times like this, and here we have on this side is the Laplacian of this. But now, since we have no fixed points, we can bound dx minus x is greater than equal to so epsilon over the compact manifold, and this term will give you t to the power 2k by b. So we say that, and since we could have chosen k over here to be anything, this gives you a bound of the form ck to the power k for any. Are there any questions? Okay. And I'll quickly do the case in which we actually have non-degenerate isolated fixed points. So now we specialize to the case in which P is an operator of Laplace type, which is the leading symbol. Okay. So, and this exercise, suppose my isolated fixed points okay. So now in this case, again we have an estimate for comma v in terms of trace of t on these fixed points, and the determinant of this form, and this is an estimate of order t to the power half. And again, this is your Atiyah-Lefschetz fixed point theorem. And again, this should remind you of the classical case where the right hand side will just compute the Euler characteristic of the fixed point set. So as I said earlier, by the asymptotics, in this case, we just need the R naught. That is on the first things, and that will be enough to give us this order t to the power half estimate. So R naught in this case is just this, because we have a leading symbol of this form, not psi square. Now E naught psi is just your integration of t lambda naught psi square minus inverse d lambda, which is just here to the power minus t square and not this is nothing but k naught t k naught. So this is saw earlier. This will just be e to the power minus psi Are you saying anything?
This e to the I, is that an inner product?
Yeah, this is inner product. X minus x inner product side.
Yeah. Okay.
Okay. So now we'll see what is the point of considering this to be non-degenerate. The condition that it is non-degenerate will now allow us to do a non-degenerate change of variables y equals dx minus x. And yeah, so what we'll do is we'll localize in a small neighborhood of our fixed point, and without loss of sanity, we take a chart such that the fixed point is t0 equals to 0, and in this neighborhood, although we can localize here because we saw that if there are no fixed points, then we have estimates to T comma P comma B in terms of order T to the power K for any K. So we can localize to a neighborhood of, we can localize in this chart, but T0 equals to 0 is our only fixed point, and we can do, and since it's non-degenerate, we can do this non-degenerate change of variables. So after doing this, change of variables, we get trace t of x as a function of y. We can invert in this neighborhood again due to this non-degeneracy condition. I y psi minus t mod psi square, and we have this Jacobian due to the change of variables. Sorry, I'm a bit over time. If that will finish in 2 minutes. Now again, we'll do a change of variables, which is to cancel out this t term over here. So we'll do psi going to t to the power minus half psi y going to t to the power half z. In this case, we'll have trace of x of t to the power half z, e of I t to the power half z psi, and this will go. So we have z and minus square here there will be inverse d psi is. Now we can compute the d psi part of the integral, and this will give us a coefficient of dx to the power half z, determinant of a minus t x of t to the power half z, and t to the power minus z square dz. Now we'll take the Taylor series expansion at t equal to 0. Since we have a t to the power half term here, we'll have an order t to the power half approximation. And over here, since t0 equals to 0, this x of 0 will be 0 over here, and hence we will just have trace of t0 determinant of I minus dt0. Are there any questions? That is the end of the talk. Any questions?
Are you done, Sayan?
Oh, can you repeat?
Are you done?
Yeah, I'm done.
Okay, so let's thank Sayan first. So I will stop the video now.